Okay, let's get started. Okay, so I uploaded the homework 4, okay, and it will be due next Friday, okay, and probably we're going to have a very short homework 5, so that will be covered the last chapter only, okay. Okay, so let's see what we cover in our previous lecture. So we start talking about lecture 9 in our last class. So we cover what is an additive noise, and then we talk a little bit on the capacity of AWGN channel. So in particular, we prove the achievability of the AWGN channel. Okay, so here is the definition of the additive noise. So basically, it means that noise is added on the transmitted signal. Okay, and here we consider everything lives in the real domain. Okay, and we let y equal to x plus z, right? And z is a continuous random variable. And here we assume the power of x is less than or equal to p. Okay, so this channel is called additive noise channel. And clearly, so the entropy, the conditional entropy of y given x equals to the differential entropy of z, right? Okay. And then we took a look at the vector form, right? Because in our channel coding theorem, everything is a vector or a code book or a code word, right? And here we let yn equals to xn plus zn, right? And now we assume that zn is an IID sequence, okay? And we're going to look at when zn is not IID either today or next lecture. Okay, so if zn is IID, then we say zn is white. Okay, so the white basically means that the power spectral density is just a constant. Okay, so that is from negative infinity to plus infinity. Okay, so it's not like in a finite range. Okay, so it basically means that in the time domain, the autocorrelation function is a delta function. Okay. Okay, so yeah, if Zn is not IID, we call that color noise. Okay. Okay, and here's the definition of the channel capacity. I mean yeah, we didn't write the definition here clearly, so you can take a look at lecture notes. So here the difference compared to the discrete case is that we have additional constraint here, right? We assume the power of x is upper bounded. Okay, so basically then the capacity would be similar to what we have defined before. All right, and here, I think here's a typo here. So I think, yeah, it should be like average, divided by n, right, this one. Okay, and then, so the capacity of this channel or the AWGN channel is given by this formula, okay? So we did do the maximization of the mutual information, right? The reason we can get this form is that, we maximize the mutual information using the Gaussian input distribution, okay? So yeah, because the constraint here is the power, so which is basically the second moment or the variance, right? And then we say, okay, if the variance is the same, then the Gaussian distribution will maximize the differential entropy, okay? And then we derive this, okay? So if you don't recall that, just take a look at your lecture notes. So, and we finish half of the proof for the channel capacity. So basically, I will finish the achievability proof, right? So the achievability is almost identical as before, right? And there's only maybe two differences, right? One difference is that, so we generate the random coding using the Gaussian distribution, okay? And the other difference is that for the error event, we have to take care of when this condition is, break, right? So yeah, so therefore, we let the power of the average power of the code word is less than or equal to p minus epsilon, right? To give a little bit margin. Therefore, by the law of large numbers, so we can show this will satisfy with the high probability as n goes to infinity. Okay, just yeah, try to recall that. And today we're going to finish. We're going to finish the proof of it. So we'll look at the converse proof first. Okay. Today is our lecture number 35. Today, number 1, so we're going to can finish the converse. Proof, okay. And then, yeah, let's see, we will talk about the capacity of probably other channel. Yeah, the capacity of other channels. Okay, so we're going to look at a number of those. Okay, and then we're done with chapter 9. Okay, for the converse, yeah, again, the procedure is pretty much the same as before. Okay, so we have what? The 5 steps, right? So, yeah, we'll just repeat the 5 steps, right? The first step is what? So assume, the message is uniformly distributed, right? And so we don't need to emphasize that, so that's the same as before. Then we can have n times r, which is the number of the indices, right? The number of source message we have. So that equals to what? The entropy of the source message. Okay, so here it's not differential entropy, right? Because we still assume the source is like, have m sources to transmit. Okay, very good. And here, so similar as before, right? So what we do is that we need to create the mutual information term, right? How to create mutual information? So it's easy, right? We just need to minus this, and then add this back. Okay, so basically the first term would be the mutual information. Okay, and how can we deal with this term? H of m given m hat. That's found, all right? So I have been using that for, I think this is the 4th time already, or 5th time. So therefore, so that will be less than or equal to this guy. And then, so I don't write the funnel explicitly, I'll just write n times epsilon sub n here, right? So epsilon sub n will go to 0 when it goes to infinity, okay? And this is the form that you'll see in almost all the papers, right? So they don't write funnel explicitly because this is so commonly used, right? So just write it this way. Okay, so if in the paper you see that, you understand, what is going on. Okay, great. So now, what's next step? Okay, so now we have like 3 steps already, right? What's next step?
Data processing.
Yeah, data processing, right? Can we use data processing? Right, so the only thing we need to check whether it's a Markov chain or not, right? So we have m, and then we encode that to xn, and then we receive yn, then we get m hat. Okay, is this Markov chain? Yes, it is, right, because the noise is independent, so that is a Markov chain. Okay, very good. So basically, yeah, it doesn't matter the noise is independent or not, right? So still, because we consider all the n together, so it is a Markov chain. Okay, so this will be less than or equal to that, plus n times epsilon. Okay, very good. Okay, so what's the next step? So just break the mutual information, right? So we're going to break it in this way. So yn minus hyn given xn plus n times epsilon n. Now remember here, so because we write the mutual information between xn and yn, so now we need to write the differential entropy. Right, so before we have the entropy, but here is a differential entropy, right? Okay, great. And and from now on, I think there's no big difference, right? So next we need to break it, right? So basically, the first term, we just use the independence bound to break it. Okay. So for the second term, right? So we can also break it, but we need to be a little bit more rigorous here, right? So basically, for the second term, we can do this. We can use the chain rule to write it out. Right, this is basically the chain rule. Okay, and because the noise is independent, right? Therefore, so this guy, this guy will equals to HYI given XI. Okay. So for the discrete time case, we use the property of the MC channel, right? But here, we also have this property because the noise are independent. Is that clear? Okay, we can do this. And therefore, so this equals to this. And then add the noise. Okay, and clearly, so now we did finish the single letterization, right? So now everything is single letter, okay, which is good. Okay, and and for the discrete case, we say okay, so each of them will be less than C, and therefore it's less than C, right? So because we define C as maximization of the mutual information, right? But here we need it more explicitly, right? So we need to keep computing that. Okay, so let's say how can we compute it? Okay, in order to compute it, so we still need this form to compute it, right? So this just to tell you, okay, so now we have the mutual information, which is good. But now, in order to maximize it, we still need this kind of form. Okay, so basically we write this again. HYN minus HYI given XI plus N times epsilon. So the reason we write in this form is that, so this is easy to compute. Okay, so if we write the other form, so this would be harder to compute. Okay, and the first term will be easier. So here, clearly that equals to H of Z, right? Because Y equal to X plus Z and given X, so this is equal to H of Z. Use the shift invariance property. Okay, and therefore, and also what we know is that Z is a Gaussian distribution, right? Then we can just write down the formula. So that's half log 2 pi E n. So we'll assume n is the variance of the noise plus n times epsilon. Okay, and then what do we do? Right, so we need to maximize it, right? So basically, similar as what we did before when we compute the compute the explicit capacity of in a discrete case, right? So basically, we can upper bound this guy using a Gaussian distribution, right? Because here, so the variance is the same, right? So basically, here we have yi equals to xi plus zi, right? Because xi and zi are independent, right? Therefore, the variance of yi so equals to the variance of xi plus the variance of zi. So that equals to p plus n, right? Therefore, here what we get. So now we assume x will follow a Gaussian distribution with mean 0 and the variance p. So this guy will be less than. And then y also follows a Gaussian distribution with variance of p plus n, right? Therefore, so it'll be less than or equal to a Gaussian distribution 2 pi e p plus n. Yeah, here we assume xi where let's say here's pi. Yeah, because so we have the constraint is for let's see. Yeah, here assume each xi is less than or equal to pi. Okay, and minus this guy. And then we plus n times epsilon, n. Okay, so this is basically, and then, so you can see that we can have our channel, right? So now we combine whatever inside log, right? So it's this guy divided by this guy, okay? So that's half log, basically 1 plus pi over n plus n epsilon n. Okay, we're almost there, right? So what we want is log 1 plus p, 1 plus p over n, right? But here is pi, right? So pi is the power for each individual xi, right? But our constraint is that the average of xi is p, or less than or equal to p, right? So what do we do? Right, so basically what we want is the average over here, but now we have an average outside. What do we do? So can we get to move this average from here to inside? Can we do that? Yeah, first of all, we don't have an average outside exactly, right? So basically, we need to, write the average outside and then move this inside. Okay, so what's that? What's the property we need to use?
Sum and log, you move the sum into a product, but I'm not seeing how that necessarily.
Yeah, normally if you don't know what to use, just remember, now we need the inequality, right? So we need upper bound, basically.
Log sum maybe?
Yeah, it's easier than that, right? Just see whatever we covered before. We only cover like 4 inequality, right? Number 1, Jensen. Can we use Jensen? Yes, right? So basically we're going to use Jensen. So what we need to do is that we need to multiply n and divide by n. Right, log sum we need, division there to use. And we don't use that a lot. Right, and here, so we can use the Jensen, right? So here we assume the Jensen, the fx is nothing but log 1 plus x, right? So this kind of inequality, okay? And the concave, right? So we can have upper bound. So basically then this less than or equal to n times log, and we can have everything inside, pi 1 over this, okay? Okay, great. So now we know our constraint is that this guy will be less than or equal to p, right? And then we take upper bound of p. So this equals to n log 1 plus p over n plus n times epsilon. Yeah, miss a half somewhere. Let's see. Okay, therefore, no, this is less than or equal to. Therefore, this is n times r, right? So this n times r less than or equal to that. Therefore, r is less than or equal to half log 1 plus p over n plus epsilon n. And this guy goes to 0 as n goes to infinity. Okay, and then we're done with the proof. Okay, so technically there's nothing really new compared to before. Yeah, right, but we just need to take care of, this Gaussian distribution and how to characterize the maximum of the entropy of the mutual information exactly. Okay, any question? That clear? Okay, great. So now let's see the geometric meaning of it, right? So before, when we talk about the DMC, the capacity for the DMC case, so we kind of explain a little bit of the geometry from the typical set point of view, right? So because we say, okay, so if I have an X distribution, and then, after the channel, right, probably we're going to see Y that is in a typical set, okay? And a given X and Y will live in a conditional typical set, right? And we use, okay, this is a total size of the typical set, and then divided by the size of each conditional typical set, and then we'll have, okay, so this is the total number of code words we can have, okay? So here we have the similar geometry explanation, right? But here it's kind of more explicit, okay? So let's see, how can we explain the capacity? Geometric interpretation. So this is a very, very important concept. We talk a little bit on this, but not in detail. But here it's more like obvious. So it's called sphere packing. So why is called sphere packing? So now we assume like it is nice ID noise, right? So basically the direction of the noise is everywhere, Okay, therefore, so we can think that the total received signal lives in a sphere. Okay, so that's it's like a big sphere. Okay, so this is all the possible signals that we can receive. So that's live in a sphere. Okay, why is a sphere? Because the noise is in all the directions. So this kind of intuition. Okay, so then we need to compute the volume of the sphere, right? So the volume of a sphere in Rn of radius r is what?
Gamma function stuff.
What?
Something with the gamma function.
Yeah, so we don't need to go into detail of that. So it just equals to Vn times Rn. So I think the key part here is Rn here. So it's proportional to the radius. Okay, so if it's two-dimensional, it's a circle, then it's something times r squared, right? If it's it's three-dimensional, is r to the 3, right? And then now we have n-dimensional, right? So this Vn is the volume of unit sphere in Rn. Okay, and normally we know this formula, okay, but it doesn't matter too much, okay? So now you can see that, so basically what we have is that, so for each signal, okay, so the radius is kind of like square root of p plus n, right? Because that's the power for each received signal, okay? So basically that is the radius, right? But now we have n dimension, so we can consider the radius in this case is square root of n p plus n. Does that make sense? Yeah, because we receive a vector of length n, right? And the variance for each of those is n plus p, right? Okay, and then the total variance is n times p plus n, right? Normally, this is a variance, right? The square root of the variance give you, the radius. Does that make sense? Right, so basically, the volume will equals to this guy to the power of n, some Vn times this, right? So this is basically the radius. Does that make sense? Okay. And now let's see. So this is the total. Based on this, we can compute the volume of the entire receiver space. Okay. So but now, what is the radius of each transmit signal? With the same idea, right? So the power for each x is p, right? And then we have a vector length n. Therefore, for each transmit signal x, so it lives in a circle with a radius of square root of np, right? And so we're going to have a lot of such kind of signal here. Okay, obviously, so all the signal will also live in the typical set, right? But the volume of that is almost the same as the volume of whatever of this square root of n times p plus n, right? So this is basically, you can understand that as a code word for the code word for each message. Okay, so now the capacity problem is to determine, the goal is to distinguish them, right? So they cannot overlap. Okay, then the capacity is nothing but what is the maximum number of sphere or number of balls here we can pack in this volume. That makes sense? Okay, so based on this idea, so we can compute what is the total number of balls we can pack there, right? How to compute it? So we know the formula of the sphere, right? So basically, let's compute the number of the small spheres. Okay, so equals to, so the volume of the big sphere is Vn multiply this, right? And the volume of each small sphere is Vn multiply this, right? So now we can see the Vn is the same because they are living the same dimension, same space. Okay, so this canceled. So basically what we got here is this guy, right? And then we take this square root out. And so inside this n can be canceled. So what we have is 1 plus p over n to the power of n over 2, right? Okay, so this is the total number of spheres, right? Okay, then what is the number of bits we can transmit? Yes?
Sorry, with the number of spheres, like, maybe this is just a too literal interpretation, but like there's going to be like gaps between the spheres, so it's not going to be a perfect package.
Yeah, so this is just intuition.
Okay.
Yeah, so of course, right? So if it's a physical 3-dimension, then of course there's going to be gaps, right? But so basically, in these circumstances, so the gaps can be ignored or is negligible. The gap would be extremely small. Okay, yeah, just pack it. Then it's not going to be perfect. Or in other words, so this cannot be achieved exactly for finite n. So it can be achieved for infinite n. You can imagine that okay, when n goes to infinity, there will be no gap. Does that make any sense? But with finite n, there will be some gap, but the gap is negligible. Okay, so this is the total number of spheres, right? But now we say, okay, so how many number of bits for this number, right? How many bits we can use to represent this number? So basically, that is r, right? So it's equals to 1 over n. We need to divide by n, right? That's a bit per symbol, right? And then we take log 2, right? Because it's bits, and then of the total number of sphere, right? And then you plug what we compute in, right? 1 plus p over n raised n over 2. This equals to this guy, right? Which is exactly the same as our capacity, right? This equals to the capacity we just computed, right? So that's the interpretation. So basically, yeah, all the capacity problem is a sphere packing problem. Does that make sense? Okay, and for the source coding, so we're going to cover that a bit later in this class. So for a source coding problem, it's on the opposite. It's a sphere covering problem. So here we see what is the total maximum number of sphere can be packed here. So that's capacity. But for a source coding problem, we want to do compression. So basically, in that case, it means that what is the minimum number of sphere that can cover the big sphere? Okay, so in the source coding context, the big sphere means the source information. When we want to perfectly recover that, so we need how many balls here we need to cover those, right? Therefore, it will be something outside, right? So that's a covering problem, okay? So, yeah, we're going to cover that a bit later. Okay, so next, let's take a look at, any questions? Okay, let's look at what's the capacity of other channel. Okay, the first example is that what about non-Gaussian channel? Right, so we assume, okay, Z is a Gaussian distribution, so why we assume that, right? So one reason is that technically it is more manageable because we like Gaussian distribution, right? Why we like Gaussian? Yeah, because there are so many nice properties of the Gaussian, right? First of all, Gaussian only depends on the mean and the variance, right? So it's very simple, right? Only the first, second order, right? And the Gaussian can maximize the differential entropy, right? So there are many nice properties of the Gaussian. But in practice, what if the noise is not Gaussian, right? And the other reason is that, okay, so we know the central limit theorem, right? If we have a lot of unknowns adding up together, it will follow a Gaussian distribution, right? But what if the noise is not Gaussian? So not all the noise in practice is Gaussian, right? It could be like, multiplicative noise or whatever, right? But here we still consider additive noise, but we assume that Z is not Gaussian anymore. Is not Gaussian, but has power n. Okay. So if Z is not Gaussian, what do you think? So you think the capacity will be higher than Gaussian or lower than Gaussian? Right? Definitely, with the same power, probably the capacity will not be the same as Gaussian, right? But do you think it should be lower or higher? In other words, the Gaussian is the best channel or the worst channel?
I mean, I think I remember the answer. So it's just Gaussian is the worst, right?
Yes, it's the worst. So basically, anything else will be better than Gaussian. So let's prove that, right? Let's see how we can prove that. Let's assume the C prime, which is the capacity, will equals to mutual information, right? So we have the PDF. So remember now, we need to maximize it with the power constraint, right? So the best distribution may not be Gaussian. Okay. Right. So then, as usual, so basically we're going to expand the mutual information, hy minus hz. So this will now be changed. Okay, for the second term, for the z, so we know Gaussian will maximize it, right? Therefore, we just take the upper bound for a second, right? So that is, we take z as a Gaussian, right? Because this will be bigger than the second term, right? Gaussian will maximize it with if the power is the same. Okay, very good. And then what do we do? So basically what we do here is that we can use the entropy power inequality. So remember what the entropy power inequality does, right? So basically it tells you that ny, because now x, so basically we assume that if either x and z are independent but they are not Gaussian, right? So basically the variance of ny will be bigger than or equal to p plus n, right? The sum of the individual variance. Okay, so that's the entropy power inequality. Okay, so from here we can show that, so the differential entropy of, the variance of y will be bigger than this guy, right? So basically we can show equivalently the differential entropy of y will be bigger than the differential entropy of x plus z, where x and z are both Gaussian. Does that make any sense? So this is basically what the entropy power inequality gives you. Okay, so remember, the entropy power inequality means that, okay, this is bigger than this, right? And so this guy and this guy are Gaussian, so this guy will be the variance, and this guy will be also the variance. Okay, does that make any sense? Okay, so basically, we can say that, so this guy will be bigger than or equal to n plus p. Okay, and then minus this. Okay, and now we can combine, right? Because we have n plus p now, so this will equals to. So that's the capacity of AWGN. Okay, now we show, okay, so if Z is not Gaussian, so this capacity is bigger than the capacity of AWGN. Okay, and this basically means that AWGN has the worst channel capacity. Okay, so this is basically for the non-Gaussian channel. And secondly, we consider the band limited channel. Okay, so this comes to the real communication problem, right? So normally for the communication problem, so we need to pass a signal through a channel, right? So what if the channel is band limited, right? So now let's consider a baseband channel. So this is related to what we cover in the communications theory class, okay? But just let me explain a little bit. So this is, let's say here is a channel in the frequency domain. So I have F here, and this is minus W, this is W, okay? So the bandwidth of this channel is basically just W. Okay, and in order to make sure the signal passing through this channel, so the maximum bandwidth of the signal will be given by this, right? Okay, so in the frequency domain, if we transmit the signal through this channel, so we just need to use the signal, multiply this in the frequency domain, and then we're done. Right? Okay, great. So therefore, in this case, so let's see how can we transfer this problem into what we know. Okay, so a key step here is what? Right, so here we need to consider discrete time samples, right? So normally what we can transmit in practice is continuous signal, right? So we need to make the continuous signal as a discrete signal. So basically we're going to do sampling, right? So but what kind of sampling rate we need to have, right? So our goal is to not lose anything, right? Therefore, so let's say if the bandwidth of the signal is W, then what is the rate for the sampling?
I mean twice, more than twice.
Exactly, with the Nyquist sampling rate, okay? So basically what we do is that we use the Nyquist sampling theorem. It's also called Shannon, and there's another name, Hartley, I guess, sampling theorem. Okay, so use the Nyquist sampling theorem. So this is to, so let's see, this is equivalently to 2 times W channel uses per second, okay, of discrete time AWGN channel. With input power constraint. So now, so let's assume that the power of X is Px, right? So this is for the continuous signal or for overall signal, right? So now, so we have 2 W samples per second, right? Therefore, so the power constraint for each signal would be what? The Px, so that's the power of X divided by 2W, right? So that's the power for each sample. Does that make sense? Okay, so this is the power. And the noise variance is given by N0 over 2, right? N0 is just a constant, okay? So, or you can understand that as what? The PSD, right? The power spectral density value, okay? So this is the power spectral density. Okay, so now we know what we get here, right? So basically, every second we have 2 W samples or 2 W channel uses, okay? For each channel use, we know how many number of bits we can transmit, right? Therefore, so now the capacity C, as before, so that's equal to this guy. So 1 plus P over N, right? So see, what is P? P is Px over 2W, right? So that's the power per channel use. And N is N naught over 2. Okay? Therefore, so we got this, right? So we cancel the 2 there. So basically what we have is Px over W multiplied N. Okay? So this is the channel capacity. Okay? Now we relate channel capacity to the bandwidth W, right? How to relate that? It's using Nyquist sampling theorem. The unit of that is bits per what? Per channel use, right? Okay, and this is the capacity of discrete AWGN channel. Okay. Okay, so but now we want to know what is the capacity of the baseband channel, right? So what's the capacity of this guy? What should they do? Okay, so the capacity of band limited channel. So what is that? Right, so this is the capacity per channel use, right? And for each second, how many channel use do we have? Two W, right? Therefore, so now we have the capacity of band limited channel is basically 2W multiply this. Right, that's equals to W times log base 2, 1 plus Px over this. Okay, so now we can say that's bits per second. Right? So that's probably, if you read any communication paper, so that is what you see there. Okay, so that's how we derive it for the band limited channel. Okay, that makes sense? Right? Okay, so now let's analyze this a little bit, right? It's kind of interesting. So we have two cases to analyze. The first one, let's say if Px becomes infinity, right? Let's say we increase the power, okay? So if Ps becomes very large, then basically means that, so this guy will become very large, right? Log 1 plus x will become log x, right? We can ignore the 1 there. So in this case, the capacity will be roughly equals to W multiplied log 2 P n naught W, right? Therefore, as Px becomes very large, so this guy will go to infinity. Right? And you can see that, so this kind of makes sense, right? Because when the power goes to infinity, then, you know, the capacity goes to infinity, right? The power is not the factor here, right? So what is the limit for this value here is the bandwidth, right? The bandwidth is a limiting factor, so we call it, when the power is large, so this is band limited, or bandwidth limited region. Okay, and another thing is that how about if the bandwidth goes to infinity? Right, so now we do not let the power go to infinity, right? We fix the power. So basically in this case, we can see that SNR equals to Px over N naught W. So this guy will go to 0 for fixed Px, right? So now let's see the capacity here. So the capacity, so yeah, we know that's a capacity infinity because the bandwidth goes to infinity, right? Then now we let W becomes very large. So in this case, because W is very large, then this guy becomes very small, right? So for the log 1 plus x, for the log 1 plus x, right? So when x goes to 0, so this guy will become what? Right? Log is like this, right? So yeah, 1 plus x, we need to shift it to the left. right? So when x is very close to 0, then the log is basically equals to x. Okay. Yeah, you can do a Taylor expansion on that, and it will be obvious. Therefore, so this equals to w multiply px n naught times w, and yeah, and if we take a log 2 here, we need to multiply log 2e. And then this equals to this bits per second. Okay, so it's proportional to px over n naught, so that's the capacity. Okay, you can see that now it depends on power. Does not depend on bandwidth anymore, right? Bandwidth is not a factor here. Okay, so that's the power limited region. Okay, so this basically means that we're going to spread the power into a very high bandwidth. Right, so any questions? Okay, next. So this is another important thing. So we have the parallel Gaussian channel. Right, a parallel Gaussian channel basically means exactly like the name. So basically we have a number of the Gaussian AWGN channel. Okay, so this is one. And then we have another one here. And then let's say in total we have n. Okay, so we just have a number of parallel Gaussian channel. Okay, and here we assume the Zn equals to Z0 up to Z1 up to Zn. Okay, and we assume that each Zi will follow a Gaussian distribution with Ni. Okay, and we assume all the Z1 up to Zn are independent. Okay, therefore in this case, Yn equals to xn plus Zn. Okay, and so far it's kind of weird, right? So just a bunch of, what we know before, right? But why this problem is interesting, right? We can just do whatever we do for each of those, right? Because all the z are independent, and there's no interference among them. They are all parallel, right? What makes this problem interesting? Two things. One thing is that so the variance or the power of the noise is not the same for each of those, okay? And the other thing is that instead of have an individual power constraint for each channel, we have a total power constraint, okay? So basically in this case, so what we're going to have is that, so this one will be less than or equal to P. So before we have individual power constraint, right? So for the power of each guy will be less than or equal to P, right? But here we have a total power constraint, right? So that's the problem. Okay, so assume this is Pi. The sum of all the Pi has to be less than P. Okay, therefore, so this problem becomes this, right? The capacity of this guy will still be the same, right, as before, but what make a difference is basically the constraint. Right, here is xn given yn because now the input is xn. Okay, so this is a basic capacity. Okay, so now the tricky part is how can we maximize it. Okay, so that's not extremely easy. So we're going to continue in the next lecture.